All right, good evening, everybody. Welcome to the April edition of the East Valley Astronomy Club meeting. So on my way here tonight, I happened to look down at my shirt and realize I'm wearing this Saguaro Astronomy Club t-shirt. And I don't know, will that get me in jail or do I go to hell or something? I'm not sure. But anyway, I guess it's okay to host the East Valley while you're wearing the Saguaro Club t-shirt. So anyway, it's actually for the Messier Marathon is what it's from. So anyway, by the way, the Messier Marathon was really fun. Friday, we got kind of skunked out there because it was cloudy. We had, maybe an hour and a half of clear, and then instantly the whole cloud just clouded over. And when I guess we're going to bed, so we all went to bed. And then the second night, Saturday night, was actually quite nice. A lot of people got over 100 of the 110 objects. In fact, one of the guys from East Valley here, a guy named Kent Bell, he actually got 109 of the 110 objects and has photographic proof to show you as well. He took photos of everything he found. He didn't get the last one because it was the first one of the evening and it was too far into the horizon to see it. And so he missed the first one and got the rest of the 109. Anyway, welcome all tonight. I see the hoodies were popular, so a lot of the folks that ordered or asked for hoodies a couple of months ago, I think most of you have got them now. The minimum order was 25. I think 14 people asked for them. So there's around 10 or 11 extra hoodies. So if you're interested in a hoodie, there are some available over there. I tried to get an assortment of sizes, so it kind of fits everybody from this tall to this tall, or this wide to this wide, however the case may be. All right, let's get going here. Let me forward this. All right, so there's the formal welcome. So as always, to those in the room and those on Zoom, and we do have several people on Zoom as well, we thank you for being here tonight. As always, I say this every month for over a year now. We hope you enjoy yourselves. We hope you learn something interesting tonight. We hope you make a new friend. And I hope you reconnect with some old friends as well. So this is where we are tonight. As always as well, please get your cell phones and either put them on vibrate or turn them off or something like that. So we don't have cell phones ringing during the meeting. So, all right, any visitors here tonight before we go on? Anybody new? If so, and would like to introduce yourselves, this would be the time. Or are we all old hat here tonight? So anyway, I guess we're all old hat here tonight. So anyway, no new visitors here. By the way, I really like that photograph. I don't know why. I think it's a beautiful photograph. So anyhow, tonight's agenda. So we have our standard general announcements, which will take 5 minutes because I've kind of shortened them up a little bit. We're going to talk a little bit about what's going on with public outreach. We're going to talk about some events that have occurred already and some new events that are coming up that you might be interested for. In fact, we have a sign-up sheet for some of the new events coming up as well. We also have a member presentation tonight. So Sid Frede is going to talk a little bit about AI and astrophotography. So artificial intelligence, or AI, is all the rage right now. Although if anybody saw the clip this week from our Education Secretary calling it A1. Well, it's very important everybody knows about A1. I thought, well, apparently you don't know anything about A1 because you're calling it A1. So anyway, so we have artificial intelligence and astrophotography. It's in everything now. In fact, I spent most of the day working and interacting with AI at my job today. Then we'll have our standard 7th-inning stretch. We'll take our 10, 15-minute break to kind of stretch, get something to eat or drink or whatever, stretch. And then we'll have our main presenter tonight. The main presenter tonight is remote. So if you hadn't seen that in the announcements, it's a guy named Vincent that is an Aurora chaser, knows everything about auroras, photographs auroras, talks about auroras, all that. And he's actually up in, well, he's from Alaska, so he's probably in Alaska right now. He is on our Zoom session. Anyway, he's going to present to us remotely, and it should be fascinating. He has an online presence, and so if you've seen any of his stuff, it's really quite interesting. So I'm really very much looking forward to hearing from Vincent Ledvina tonight. All right, general announcements. So if you are a joiner, you can join the club. It's a good time to do that. You can join online, or you can join by talking to Brooks at the back table back there, and he'll take your payment or whatever else. Membership is very important to the club. It forms at least a third of our club income. And we're announcing a trip tonight that's going to be available to all of you. And part of that trip is going to be subsidized by all of your dues. And part of it, we're going to ask for a little bit of cash as well. But it helps, or all the snacks and the sodas on the back table, or all those sorts of things. This is all because of, or partly because of your dues. So it's very, very nice that you're members and that you pay your dues. It helps fund the club and what we do. It also, just your participation also helps us do a lot of other things. We have a public outreach that's very active during the cooler months of the year, and we couldn't do a lot of that if we didn't have your support here in the club. And so Alice will be talking a little bit later on about what the events have been and the outreach of programs have been for this last month. So you'll hear a little bit about that. We actually tried something new this last Star Party, so she'll be talking about that as well, and it went really, really well, and you will have a part in that as well. If you'd like to know what's happening here at EVAC, there's at least 4 different ways you can know. Some ways are kind of pushed on you, and some ways you have to go out and hunt the information and pull it in yourself. So one of the things you can do is you can sign up for our email distribution list, and anything that happens that we think you need to know about, we'll go ahead and we'll email it out. Like I emailed out about the meeting. Amanda, our vice president, emailed out about the meeting. I emailed out that the hoodies were in and available for everybody. So things like that. We never put your email on any other site or give it to any other company. So no spam from us. Our list is private just for us. If you still don't want to do that, you can always go out and manually pull the information yourself by going out to our website and looking on our events calendar. And anything you see out there on the events calendar, if you click on it, it'll bring up some details and tell you the details about it as well. We can also have you either automatically or manually get our newsletter each month. And if you sign up for our mailing list, you get it automatically, but you can always go to our website and pull it down manually as well. And it'll tell you what's going on with the club as well. And then you can also get some EVAC and member announcements by joining the East Valley Astronomy Club Facebook page. And it has over 1,000 members. And so people will post their astrophotography pictures. They'll post their telescopes for sale. They'll say, hey, we're going to Picket Post this weekend. Anybody want to go? That's what James does all the time. Hey, we're going to Picket Post. So anyway, that's available to you also. If you need a telescope or any kind of training on how to use a telescope, we make that available as well. We do have equipment for rent and for sale. We're always talking about, do we need more? Do we need something different? And so we're always looking at that. And we have everything from push-to-go scopes to go-to scopes to we even have a C-Star you can rent. And the rental prices are super cheap. They're $25 for a week. So it could be a kind of a try before you buy kind of thing. So very, very inexpensive. And we also have equipment for sale as well. I know this week or this month, we got what, maybe 4 telescopes came in roughly?
We sold 4 in the last couple of days, but there's still some more.
Yeah, we had 4 come in, just donated to us this month. And James just said we've sold 4 of them already. So anyway, and the nice thing about these scopes, they're in pretty good shape, or James doesn't sell them. And the other thing is they're about half price of what you pay retail for them. So it's a nice way to get into a telescope without having to spend a ton of money. So that's available to you as well. We also have some online training you can look at on our website. Each of those 30, well, there's not 33 there, but there are 33 boxes on the website. Each one will tell you a little bit about some area of astronomy, and you can read about that. And then James also teaches a class 2-3 times a year. He has a beginning telescope class, which is, have you finished yet, or you're still working? Okay, finished the last class, and they've got one more lab left. He also does a beginning planetary astrophotography class as well. Anyway, how many did you have this time for the beginner's class? 35? 20 some. Okay, I thought it was a little higher. But anyway, yeah, a very popular class, obviously. All right, let's see. Hoodies are here, as you all know. So there they are. And there's my stunning figure. So anyway, there's the hoodies. And we do, once again, have extras. So if you would like a hoodie, they're zippered and whatnot. Go over there, and Alice and Gordon will take care of you over there tonight. And Brooks will be happy to take your payment there in the back room. Our charter is always giving back to our community. So Alice, that's your cue. Alice is our events coordinator as of a few months back and has been doing a wonderful job for us. So take it away.
Thank you, Steve. Yes, my name is Alice Clove, and I am the EVAC's Outreach Event Coordinator for our chapter. So the nice thing that we have is we have two ways with which we can give back to the community and share our love of astronomy. And the first one, let's see if I can remember how to do this. Yes. All right, our first way of giving back is just right over at the Riparian at the Greco Observatory. So what is this all about? Basically, it is you can get trained to operate the telescope. If that is not your thing, you can work the door, which is just basically we keep track of how many people come in to observe, and there's a little clicker and you click on that and you just talk with the public. Or my favorite thing that I love to do is entertain. If there's a long line, I just entertain the crowd, basically teach them telescope etiquette, what we're viewing, maybe a little 101 class, like what's the ecliptic, where's the Big Dipper, that kind of thing. So if it's something that you're interested in, there's the email that you can email Claude. He's the manager, and he'll be happy to contact you back and get you trained if that's what you want to do for the telescope, or have you come out and see what it's like to work the door or entertain the crowd. It is a really fun way. I've enjoyed it so much. Gordon and I volunteer out there at least twice a month. I learn a lot from our members, and I also learn a lot from our guests. Now on to my gig. All right. The next way to give back is through our outreach program. So this is where we go to communities, public places like HOAs, libraries, schools, and we share our love of astronomy with the guests there. So what does that entail? Well, I need two types of people. The number one is what I'm calling walkers. And there are people who just kind of keep an eye on the guests, maybe remind them of telescope etiquette, keep the kids in line. So that's a big help. Also, our astronomers with their telescopes, making sure they're doing okay. And then the next would be an actual astronomer with their telescope. You bring your telescope out and you have maybe one or two items in mind that you're going to look at, and you share that with the guests that are coming up. I absolutely love doing this. This is my favorite part. To hear the oh wows from everybody is amazing. So it usually is about an hour to 2 hours at the max at these parties. You get to choose what you want to go to. The same with Greco. You get to choose what days, how often, that kind of thing. And if you are interested, be sure to sign up on the free list mailing list, because that is how I send out what's coming up for the next month, what events are coming up. Also update you on if there's any changes or cancellations. Also to remind you, hey, tomorrow night we're going to have a star party. So if you want to do this, definitely sign up on that mailing list. I also want to do a huge shout out to all of our volunteers that have supported us so far this year. Your time is the most valuable thing, and the fact that you give of that time is very appreciated, not just by myself and by the club, but by all of the guests that you inspire, that you bring joy to when you bring your telescope or you come and you help out. So thank you so much to all those who volunteer your time. So we're going to share Leading Edge Academy. This was the one Steve was telling you about. Now, the sky was a little iffy. And so again, I sent out an email and said, hey guys, let's be a little flexible. We had 3 telescope operators that were down, possibly viewing, which we were able to view in between clouds, but we really didn't want to cancel. So we set up a booth. So we had Amanda and Gordon and Brooks. They all were manning a booth with telescopes and showing different types of filtering and the meteorite display. And there's Brooks with the meteorite display, which thank you, Brooks. That meteorite display is always a huge hit. And then thanks to Steve, he thought of something pretty cool. We had a moon globe and we put the moon globe way on the other side of the room. And he was using the telescope to show the kids and parents and teachers, hey, this is how we view, just in case we couldn't view outside. And then we did have 3 telescopes outside that we're viewing. Let's see, it was David, Josh, and John. So they were able to view Jupiter and the moon through the clouds. Everybody was super excited. The principal was so impressed with us that we received this amazing email. So I actually have been in contact with him and we're looking to book again for his 2nd annual star party. So pretty amazing. And then our 2nd Friday star party last week, finally. I've had to cancel the past 2 months due to weather, but again, a great time. In fact, there's a guest here tonight that I met her at the star party and told her about coming tonight. So thank you for coming. And again, at these star parties, we meet wonderful people and learn a lot. And then here is our upcoming star party events. Our season's kind of winding down. We have 3 coming up, 1 next week, 2 the following week, and then it's 2nd Friday star parties for a couple of months until I think June. We have the Multi-Generational Center in Apache Junction, but if you're interested and you're new to the outreach, again, sign up for those free lists so that you're included in the emails, and then I send out reminders and then also on the calendar. So if you guys have any questions, please feel free during the break or after the meeting to come up to me and ask me. Thank you, guys. Here you go, Steve.
All right, thank you, Alice. Appreciate that. I'm like Alice. I like entertaining the crowds at Greco more than I like operating the telescope. I have operated it many, many, many times. I've managed it a few nights a year here and there. I like working the door, that's fine, but I love standing out on the ramp where all the guests are lined up and talking about Betelgeuse or, you know, whatever it might be in the sky that night and giving them facts and figures and information, explaining how the North Star works. I love doing that kind of stuff. It's a lot of fun. Anyway, all right, events, past and upcoming. First of all, the Saguaro Astronomy Club had its Messier Marathon this past month. Once again, there's the t-shirt. So as the saying goes, been there, done that, got the t-shirt. So anyway, so there's a few of us just kind of hanging out at the marathon, just a few pictures here and there. We're really roughing it. We're having our wine and cheese and bread there next to my tent. So we were really roughing it. It was tough. So anyway, and then we're starting to set up. So you can see some folks there. In fact, that's what Jeff and Andrea and James and various people there. And the weather, as you can see, was a little iffy. That was a Friday night picture. You can see the clouds. So we like I said, Friday was a little bit tough, but Saturday was actually great out there. Anyway, it was a lot of fun. We had a good time. I asked Alice specifically for that picture off of her sea star because that was my favorite object of the night. That was M3. It's a big globular cluster, and it was beautiful. I love that globular cluster. So anyway, she took a picture of it for me and got it on her sea star. I appreciate that a lot. Anyway, just some people setting up there again. And oh, that's Kent. He was the one that got 109 of the 110 objects there. He was set up just on the other side of my tent. So we spent a fair amount of time talking. Did anybody attend the Fountain Hills Dark Sky Festival? And would you like to say anything about it? I'll give you the mic for a minute if you'd like to. I'm not going to put anybody on the spot. You would, Steve? Okay, I'll hang on. I didn't get to go because it was the same weekend as the marathon, Messier Marathon. So,
yeah, I attended the Fountain Hills Dark Sky Festival, and I got there actually a little bit later. It was about twilight when I got to set up. And there was a ton of people there. I mean, from the time I set up about 6:30 till the time I knocked down at 9:30, it was just a constant stream. I only did one object all night, and I probably had 15 to 20 people in line constantly. And they also had some speakers from NASA that were there, and then some also astronomical exhibits that were in one of the pavilions. But all in all, it was a pretty good time. And I got to thank James Yoder for coming up with the laser that fits in the focuser, because I got there late and I didn't have time to set up to adjust my Telrad and right angle finder scope. So that saved the day.
By the way, as I got out into the crowd here, I noticed another Aurora Astronomy Club t-shirt. So apparently we're going to jail together for being at an East Valley club. So anyway, all right. Thank you, Steve. Appreciate your little recap of the Fountain Hills event. All right, so a little something new here. We have a new tour available to you. You can sign up for it tonight. And so we have actually contracted to get a bus. So we are going to take a bus load of people down to Tucson, at the University of Arizona down there. And you can sign up for one of two different tour packages. One's probably a little bit more hardcore, the one's maybe a little bit softer, but tour one, we can only do 30 people max on that tour because it's going to two different places down there in Tucson. First of all, it's going to go to the what they call the Space Imagery Center. I'll talk about that on a future slide. And then it's also going to go to the Richard F. Karras Mirror Lab. And I'll talk about that in just a minute as well. Of course, then we'll do lunch in Tucson when we're done. Lunch will be around 1 o'clock. And then the bus will bring us back up here and we're going to drop off and pick up right here at the library. So it's nice. You know how to get here for this. You'll know how to meet the bus because it's the same place. There's the second tour available as well also. This is the University of Arizona Science Center, and I'll talk about that in just a moment as well, followed by the Flandau Theater Planetarium, then lunch with everybody. Tour groups 1 and 2 will combine for lunch, and then once again, we'll all come back by bus. Anyways, what are these things? Well, the NASA Space Imagery Center is actually on the University of Arizona campus, and it's basically a facility that's one of several that NASA uses to sort of archive decades and decades of space photos, pictures, all sorts of things like that. They don't normally do tours. It's kind of a NASA thing, but I talked to them for a little bit. And they said, well, if you want to bring a group down, yeah, we'd love to do a tour. So anyway, so they've agreed to meet us there on a Saturday because they're not working on Saturdays, but they've agreed to meet us and allow us just to browse through their this massive archive of photos. The guy said I could spend all day just on the lunar photos. They have decades of lunar photography from not only the Apollo astronauts themselves, but from like the Lunar Reconnaissance Orbiter and things like that. There's pictures from Mariner, there's satellites, there's pictures from the Pioneer satellites, just all manner of stuff there. Apparently there's literally tens of thousands of images and photos and stuff you can sort of sift through. The guy says it's absolutely fascinating. So that's one of the things that's available in tour number 1. The other thing would be then the Richard F. Karras Mirror Lab. And this is a facility that builds professional mirrors for large observatories. They're currently, I guess, making essentially 120-foot diameter mirror right now down there. So anyway, so we'll be able to tour that one as well. And once again, the Mirror Lab and the Space Imagery Center, we can only accommodate 30 people because of the facilities we'll be touring. But also, you can also do the Science Center down there and their planetarium if you want. Now, we did the ASU planetarium, but it was more of like a movie with 3D glasses. This is actually a real like domed planetarium where they project the sky on the ceiling and you lean back and you're laid back in a chair and all that. And I've been reading up on planetariums. It's listed as one of the top 10 in the US. So apparently it's a nice planetarium and it's in their Science Center. The Science Center not only has space stuff, It's a little hard to read, but up in the kind of the top left corner there, I can read it too if you can't see it. They have the universe of science, the undersea discovery, the wild world of bugs, sharks, magnificent and misunderstood, high rise, the eye in the Martian sky, solar system revealed, destination Mars, the fossil corner. They have all sorts of stuff at this thing. So if you would like to, bring like one of your children or a significant other, this might be a nice place to go and spend a day because there's something for everybody at this science center. And then once again, there's the planetarium show as well. And so you'll have that option as well. In terms of the details for these two things, for the Mir Lab and Space Imagery Center tours, this has all been set up for Saturday, June 28th. So that's the date. The bus will leave from here at the library at 7:45 in the morning. We'll get down there. We pretty much tour and do the tour or the Space Center and our Science Center and the planetarium from 10 to 1. We have lunch, just maybe about a block off of campus. There's a lunch place we'll go to. And then we'll jump back on the bus. It'll bring us up and drop us off at the library and the day is over. Getting a bus was a little pricey, but anyway, we've got the cost down to about $40 per person, so it's not free like the ASU event was. ASU was very expensive, so we kind of shot the wad on that one. But this would include your transportation down there and back, 2 tour tickets, whichever tour you sign up for, because there's tour group 1 and tour group 2. And then, of course, lunch as well. So anyhow, so that's available to you. If you're here tonight, there is a sign-up sheet back on the table where Brooks is at. And you can sign up your name, your email address, so I know how to get a hold of you. And then you check off which tour you might like to go to. Now, we're going to try to accommodate members first. So if you're here, but you're not a member of the club, it's not you can't sign up. It's just that 30 members sign up before they're going to get to go first because they're members and they're paying dues, and that's just the right thing to do. We're also going to allow the members to have a +1. So if you'd like to bring your significant other, or like I said, one of your children or whatever, particularly for like the Science Center or whatever, then you can do that as well. Anyway, so there's sort of the schedule for it all. We would like you, if you're going to do this, to have your payment in by May 16th. Now, why May 16th? It's basically the next club meeting. And it's a month before the event because we had to pay out some money to reserve the bus and reserve some tickets at various facilities, but we haven't paid everything yet because we want to see how many signups we get. I did ask about this, by the way, 2 months ago. A lot of hands went up, so hopefully we get a lot of follow through from all those hands that went up when we asked about this. The information for the Science Center and the planetarium is almost identical because it's all the same bus. The only difference is you're going to a different venue when you get down there. The bus actually will drop us off at the Science Center. The Mir Lab is a couple 100-yard walk away. So it's all kind of right there. And the Imagery Center is right there as well. So there's maybe a couple 100 yards of walking between buildings, but that's about it. Oh, by the way, I need to back up a little bit here. If you're going to be doing the Mir Lab, notice there is some requirements there: flat, closed-toed shoes. And there are some stairs because it is a manufacturing facility, and they do not allow bags on the inside, but we do have a bus. We can stick stuff on the bus and it'll be safe on the bus. So anyway, so a couple things there. Anyway, this is, like I said, June 28th. That's a Saturday. If you'd like to go, please sign up on the back table. And if you're online tonight, you can email me and I'll set up with you online for that reason. So anyway, all right, so those are available to us. We are now at a member presentation. So where did Sid go? Up right there, okay. So we have a member presentation from Sid Frede. He's gonna talk a little bit about AI and astrophotography.
And forward is just down. Good evening. I'm Sid Frede. I joined East Valley Astronomy Club right before COVID. And at that point in time, I got involved in pursuing astrophotography. I had my Canon DSLR. I attached it to a 6-inch Meade SCT scope I had and started taking my first photographs, and I got hooked. And from there, I continued on and added a couple of telescopes, and now primarily stationed in my backyard. And over that period of time, there's been a tremendous change in the way we can process those photographs that we take. We spend a lot of time in taking photographs. You know, I typically in my backyard in Tempe in Border Lake skies, spend about 20 hours of exposure on a target to get some decent data to process that photograph. So to do that, it takes a lot of energy and a lot of effort. So let me get started here. What I want to talk about tonight is basically how artificial intelligence software tools have helped accelerate amateur astrophotography and professional as well in being able to process those images in record amount of time with extreme clarity. Specifically talking about a few things in general, which these are things that usually occur on the front end of a process when you first get the data from your telescope and you start processing it to try to create that image. Basically, it's revolutionized the field of astrophotography processing and makes it more accessible, efficient to the amateur and the professional. And specifically, I'm going to address some AI power tools this evening called GrAxpert, Star Exterminator, Blur Exterminator, and Noise Exterminator. These are all artificial intelligence generated tools that are available to the amateur astrophotographer. And they're really concentrating on talking about smoothing out gradients of a photograph, enhancing the structure, extracting and processing the stars and the images below those stars, and reducing the noise in a particular image. Resulting in it's a more accurate, sharper, and it's a more detailed image. So the first steps in processing an image take a significant amount of time and effort. And the processes I'm talking about this evening can easily take 6 hours or so in trying to adjust those particular processes to get started really in processing and making the image. These AI tools are appropriated very early in that process, and literally you can reduce about 6 hours of what we used to process time into about 15 minutes. And I have a short demo at the end that shows the actual processing of these steps on a particular tool. And also one important thing to talk about is that it helps removing the guesswork from processing an image, and I'll show you where some of the guesswork is involved from an individual. And really it relies upon that artificial intelligence, the neural networks, and heavily intensified math. So gradient correction, deconvolution, star extraction, and noise reduction are the things specifically we'll talk about. So let's look at the first one. Light gradients. When you take an exposure, the background of that exposure is going to be affected by a number of things. Typically, to make an astrophotograph, we take long exposures, a minute, maybe 3 minutes, maybe 5 minutes, maybe 10 minutes. So the light variation during that period of time can alter itself significantly. So also we do multiple nights, maybe multiple days of exposure, multiple weeks. We might even take some images we did a year ago or a couple years ago. That same target comes in the sky, so we'll take some more exposures. We'll add that to the previous exposures and create a new image. Changing sky conditions, obviously seeing changes during the night. Position of our image will start hopefully out in the east. We'll track it across the sky into the west until it disappears if we follow it all night long. The moon obviously has an effect depending on where the moon is and the intensity of the moon, and a whole number of other things can affect that. Light pollution certainly has an effect. Certainly if you're trying to photograph here in the city environment, light pollution can be critical. And also clouds, very unpredictable, and they do show up and affect the image. Deconvolution, it's basically a mathematical process that helps bring out portions of our image that exist, but that are difficult to see. And we'll talk about that a little bit as far as giving you an example of what that looks like. You take a look at some of those issues. It's better to show an example rather than trying to discuss it. And star extraction. When we're processing an image, we have stars and we have structure underneath. And typically we'll process the structure and the stars in a different mechanism. What we try to do is remove the stars from the image and process them separately, and then recombine them later on for the complete photograph. That can be very difficult to isolate the stars when you're trying to process the underlying nebulosity or the other structure of the image. So this is a technique that you need to do to be able to complete that photograph. So let's take a look at what gradients and what I'm talking about here. If you look at this photograph, this is the combination of the initial image And you can see that, and down at the bottom part of the photograph, we have some off color, maybe a yellow or a greenish tint. And the upper part of the photograph is a different color. This is prior to doing gradient removal. What we're trying to accomplish is starting out with an image in the background that has a fairly constant background intensity. In this particular image, we remove the gradients, so you can see the background is constant, and there's no light variations across that image. So now we can start with that and use that as a basis to process the photograph. To achieve that previously, there was a tool, and I'm primarily a PixInsight user. If you're familiar with processing, PixInsight is one of the leading software tools in processing astro images. This is a particular tool within PixInsight called dynamic background extraction. They tend to like make up big names for some of the tools, but you can see some of the things that are usable. We have a number of boxes here that you can change the parameters, adjust all these parameters, and what we're trying to do is select individual points within our photograph that represent kind of a neutral background. And if we select enough of those points and let the software do its work, it then does that gradient extraction for us. Well, all these particular elements are something that the user can adjust. So what it becomes is kind of a guessing game. Try this, see what happens. I didn't like that. Try this to see what happens. I didn't like that. Try this to see what happens. I didn't like that. And this process can literally take hours to finally come up with something that you feel has accomplished the gradient removal that you're trying to achieve. Consequently, there's a program called Graxpert, which is an AI generated program. And this is what Graxpert looks like. What's my image? Am I going to do a subtraction or a division? And what intensity? I click the red or the green check marks, they go, and it takes care of the rest of it for me. And literally in a few minutes, we'll do that process, which otherwise on the long form, it might take me hours to accomplish that. Pardon? It's a plug-in to PixInsight. These are all tools that can be operated within the frame of PixInsight. Deconvolution is a little more difficult to really take a look at. What we're really trying to do is to very subtly find structure within our image that does exist and then bring that out to the format so we can highlight that. It's more difficult perhaps to see, but if you'll notice from this photograph to this photograph, the stars are a little better defined, a little crisper, and they start to see a little more structure appear in a location like this and like this, where we see some other nebulosity that's more defined. This is kind of a close-up of a section of that drawing or that photograph. And here you can see the definition of the stars. The star becomes a little more crisp and the background becomes a slightly better defined. So oftentimes that change is subtle, but it can add a lot to the clarity and to the structure of an image. Also, there's something called chromatic aberration, which affects the stars, especially when you get under the perimeter of the image that you're looking at. This process helps to remove some of that chromatic aberration mathematically. And this is a little bit of an exaggeration, but it helps us get that pinpoint round star that we're looking for, which stars are supposed to be round. They're not supposed to be like this. So the previous method, again, within PixInsight, we have a particular tool that has a lot of particularly adjusted parameters. And that's the same type of the thing where you can, I'll try this and see if it worked. I didn't like that. I'll try this and see if it worked. I didn't like that. I'll try this and see if it works. I didn't like that. This process can take a long time. And frankly, the results are very difficult to achieve. And probably most amateur astrophotographers don't bother. This is a process that's too complex, that doesn't really yield the results from the effort that you put into it. And for that period of time early on, a few years ago, when I was trying to experiment with deconvolution, I tried to do that particular process, and it was just too difficult. It just didn't work. With AI-generated processes, this is called Blur Exterminator. We have a couple parameters here where we can talk about the sharpening of the stars, how we want to concentrate those stars, and a couple of parameters that really work on the background of the nebulosity. So we adjust a few of those parameters and click go, and it's done. It'll take a few minutes, maybe 5 minutes to process that image. And again, we've achieved that particular activity, which may have taken a long period of time before, which may have not really worked. unless you're really, really good at it and spend a lot of time at it. Star extraction. This was the image we saw before. So this is what we're trying to accomplish. We pull the stars out of that image, and now we can concentrate on processing the nebulosity and the structure of that image. We can take the stars and process those separately. We can adjust the contrast, the hue, the intensity, and then when we're satisfied with those, we'll set those aside. And later on in the process, when we're finished working with this, we'll stick them back together again for the final photo. It makes it much easier to do that. What we did before in PixInsight, we had a tool, we basically create a star mask. And what a star mask is the software tries to identify every point in our image that thinks it's a star. So it makes a mask so that when we work on the image, we can not affect anything that we do to the image to that area that we eliminate with that mask. When we're through doing that, we can invert the mask, and now it's protecting the background, and now the stars are available, so now we process the stars. We talk about hue and contrast and clarity and all those types of things we're working on. To do that, again, we have a bunch of checkboxes with a bunch of variables that we try to experiment to get something that works for us. It'll work pretty well. Most of the time it does. It takes some time to do that. With this particular process, this is what we do. We click generate a star image, click go, and what you saw before, it separates the stars, separates the image, and we can work on them separately. Noise. Noise is a killer for an astrophotographer. It's always there, always difficult to get rid of. This is an example of a section of that drawing we saw previously, that photograph, and here we're looking at the background noise of that raw photograph. And this is what we see when we finish with noise reduction. That noise is gone. And now we have a base photograph that's very easy to work with. The noise is no longer a factor, and we can build on the image from there. Previously, not only do we have one particular tool with a whole lot of variables, now we've got a couple of more tools with even more variables, and good luck getting it right. It takes a long time. You have to really know what you're doing, spend a lot of time on a lot of YouTube videos trying to figure out what people are saying. And of course, everyone you listen to is going to tell you something different. So it winds up being experiment again. I'll try this and see what happened. I don't like that. I'll try this and see what happened. I don't like that. So that process could take a long, long time. The AI tool looks something like this. How much of the noise do we want to remove? And typically you don't want to remove 100% of it because that makes the photograph look very flat and not very natural. So typically you're going to have something in the 85% range. Again, pull that over to the image, the noise is gone. Try a little demo. This is what we're looking at is something called SH2-254, often called the Mushroom Nebula. And this particular image, I took 3 filters, sulfur, hydrogen, and oxygen, 75 of sulfur, 72 of hydrogen, and 76 of oxygen. All those are 300-second exposures for a total exposure time of about 18 hours on the target. So what we have here, this is our initial sulfur image, hydrogen image, and oxygen image. We're going to combine those into an image we call the SHO palette, which is the Hubble palette. Those are the filters that Hubble uses to take its exposures. And we generate a color image that we'll then process. To start out with, there's something called an image container. And I basically bring into that image container my sulfur, hydrogen, and oxygen filters. And then everything I work on, we're going to do sequentially on those particular devices. So let me see if I can get that to run. And if I'll show you here, where's my, it was there a moment, there we go. If you take a look here, if you can see that, this video is going to run about 2 minutes. And this is the actual processing time of all those things we just talked about. So let me go ahead and kick that off. So here we're taking those 3 images and we're dragging it up to our Graxpert, which is our gradient removal tool. And it's starting now to crank and do the gradient removal on all 3 of those images. It's also going to show us something that's kind of a background map of what those gradients look like. If you'll notice, this particular oxygen has a very dark corner up here in the upper right. And this is our gradient mask for the oxygen, so it tells us where our gradients are. And when we're all through, we see now we have our 3 sulfur, hydrogen, and oxygen with nice flat neutral backgrounds. We take those 3 images, combine them into a color image, and this is our Hubble palette image. I didn't like the way it looked orientation-wise, so I rotated it 90 degrees. And then we went up and did blur exterminator, which is our deconvolution. So if you take a look kind of at the changes in the stars, which is most obvious as it runs and completes. Stars are now smaller and crisper, a little bit more structure in the nebulosity. We did the star extraction now. There are our stars, and here's our image. So we'll process those separately to get our final image, our final photograph. And you can see now, here's that noise I talked about. So now we'll go pull noise exterminator over. And it's processing now and running in the background. And again, this whole process of all these took about 2 minutes. And there's my image with the noise removed. And this is the history of what we did. There's the rotation, there's the deconvolution, there's the star extraction, and there's the noise extraction. And that's kind of a close-up of some of the structure. But that all took just about 2 minutes. And the manual process, as I talked about before, literally would probably take about 4 to 6 hours to do that without AI. And let's see if we can get to the next one. It wants to run again. Is there an easy way to get to the next foil? We can watch the 2 minutes over and over. We're stuck in a loop. Here we go. Even by running it 3 times, it took us a lot less than 6 hours. This is a variation of the image that we just did, the final image. And what I did is I created some other palettes, and I called it my magic mushrooms. For any of you that grew up in the 60s and 70s, you may recognize these. But just kind of shows you what we can do. If you take a look at some of the detail now, and the contrast is available in the mushrooms itself, we have some areas of dark nebulosity there, some more structure. And you'll notice that our stars now are somewhat reduced and fairly round and small. So that's kind of my final interpretation of that particular image. This is another image which was a color image, RG and B filters. This is the initial image we started with after they were first combined. And this is the image that I wound up with. Lots of structure now in the arms. All the pink and reddish areas are concentrations of hydrogen, which are very active star forming regions. But without the AI tools, I could never have gotten to here. And that's it. Really, the AI tools allow you to get rid of some of the laborious tasks and really concentrate on what astrophotographers want to concentrate on, and that's making a pretty image. So you can spend most of your effort in creating something that you like, that you want to present or put up on website someplace or put it in your files. Any questions I could answer?
Why do you choose noise exterminator after you do the star? Why don't you apply noise exterminator before you do the star?
Noise exterminator is something that can be used either in a linear format, if you're familiar with processing, or a nonlinear format. And Russ Crowman is a gentleman who generated a lot of these tools, and that's sort of his recommended flow as far as when to apply that. Typically, you're applying noise extermination a little later in the process, or maybe even after you've gone to the nonlinear process, especially when you're doing deconvolution. Deconvolution depends upon the presence of the noise in the original image to very specifically calculate the point spread functions of the stars, so it gets an accurate representation.
Regarding the gradient removal, are you doing flat fields and then gradient removal on top of that, or with your narrowband images, do you skip flat fielding?
Just doing a narrowband, combining the narrowband filters and letting the gradient removal take over. It takes care of all that.
Do you run the blur, or rather the gradient, for every session? Like if you were dealing with a different phase of the moon, you had different data accumulation conditions, would you run these processes separately for different sessions?
Not quite. Are you talking about planetary type stuff or deep sky?
So you said you're accumulating 100 hours.
Right.
It's over
Yeah.
a month.
Yeah, I'll take those images, and whether it's a couple of nights or a couple of weeks or even years, and you run those and you'll stack those images. So you'll wind up with a master image that's a result from the stacking of all those images, and that's where this starts. So I have a master image for the sulfur, a master image for the hydrogen, and a master image for the oxygen that were built upon those 75, 72, or 70, whatever it was, number of images that were taken. So when those are stacked together, I wind up with one image for each filter.
But if the conditions change and one night there's no gradient, and then you're combining data that has a gradient, you're just combining it all and saying, okay, take out whatever there is.
Yeah, when you wind up stacking that image, you'll get the good nights and the bad nights, and you wind up with a gradient from your final photograph, which is going to be representative of the time that you spent imaging. Yes. Okay, thanks a lot.
We have a speaker tonight. It's a gentleman named Vincent Ledvina. You might be aware of him. He has a large online presence where he's known as the Aurora guy. He's also currently a PhD student in astrophysics as well. So he does classes by day and auroras by night, I guess. So anyway, he has about 36,000 followers, for example, on X right now. So he's very, very popular. Anyway, I'm assuming he can hear me. He's in the meeting now. Yep. And take it away. We can hear you. You just said yes.
Right.
And
Yes, I did.
We could see your display on our whiteboard. So take it away. I'm going to let you have it now.
All right, sounds good. Yeah, thank you for having me. Really stoked to be here and to speak to all of you. My name is Vincent Ledvina, and I'll be talking about chasing the Aurora, nature's most spectacular light show. So we can take questions at the very end. I have about a 40-minute presentation, and that'll leave us roughly 10 minutes for questions, and we can spill over if we need to. So let's take it away. So here's a quick outline of my talk. I'll first go into who exactly I am because, I guess if you follow me, then you probably already know. But if you don't, I'll just share a little bit about my story and how I came to chase the Aurora, and then I'll delve right into the science of space weather and auroras. When the sun gets angry, so when space weather rears its head, and you could potentially get aurora down in Arizona. We'll talk a little bit about forecasting the aurora, some chasing tips and tricks, photography, time-lapse, real-time video, and if there's time, I'll show you some of my favorite aurora photos. So a little bit about myself. Like was said, some people call me the Aurora guy. It's a name that I got when I was actually at the University of North Dakota doing my bachelor's in physics. So I moved to North Dakota. I'm originally from the Twin Cities in Minnesota. So I've only been in Alaska for 3 years, actually, but I love it here. And yeah, I guess I just got this name, the Aurora guy, out of chance. I started sharing my photography on social media, and that was just the name that was given to me. And at first, I was, a little bit shy about promoting that, but people said, no, this is just what you do, so you should just, take it and run with it. So that's what I'm going to do. And I live in North Pole, Alaska, and I say that because it's just kind of a cool name. And whenever I travel outside the country, people always think that I have a fake passport because it says I live in North Pole, and apparently they don't believe that, that's a real thing. So being in Alaska, I moved here to go to school. So I'm doing a space physics PhD program. So space physics is kind of like astrophysics, but it's everything inside the solar system. So really, it's everything that you don't see and that most people don't care about, which is all the stuff in between the planets, all the space plasmas. So that's what I'm studying, and that also includes the aurora, things like the ionosphere, the thermosphere, the exosphere, all the different spheres, heliosphere. So I have about 3 years left in that program. I'm a professional aurora chaser. I run tours and workshops and all that in my free time. I'm an intern, so kind of at your latitude, down in Los Angeles at the Aerospace Corporation. So I'll be back down there again this summer. And I'm really passionate about citizen science and science communication. So here are just some quick slides. Aurora chasing adventures through the years. This was back in 2022. I went to Churchill, Manitoba, which is on the southern shores of the Hudson Bay, and spent a week up there aurora chasing with some friends. And it's a very different kind of experience, aurora chasing up in Churchill, because you have to worry about these guys here on the left, these things called polar bears, which are a little bit more unfriendly than the bears that you're maybe used to, black bears and brown bears. And we saw a bunch of them when I went back in September, a little bit too close for comfort in some instances, especially the one on the left there. That was actually just, we had just enough time to grab the camera, but we almost actually hit that polar bear. It was in the road as we were turning a corner. Then the one on the right was one that we actually saw as we were changing locations from one place to another. So, when you're out aurora chasing in Churchill, you kind of scan the horizon as you're driving. Somebody sticks their head out the sunroof and, with this spotlight kind of scans the tree line to make sure you don't see any eyes. And we thought we were good. And then, of course, the moment that we left, polar bear was in the road. And we were like, wow, that was a little scary that we didn't even see that thing. So, but in Alaska, the auroras are amazing, far different than maybe what you're used to at mid-latitudes in Arizona, or even if you've, been to other states like Minnesota or Wisconsin. In Alaska, in Fairbanks, the aurora is right overhead, and we get it every single night as long as it's clear and dark. So, right now it's April 18th. So I'm actually in Anchorage right now. I'm just here for the weekend, but the sun doesn't set until about 9:40 p.m. and it rises at like 6:30. So we've already lost our full night, and we're going to be losing our astronomical twilight in about a week. So it's impossible to see the auroras after about 2 weeks. In Fairbanks, even at the dead of night, it's just not dark enough. So aurora season is really from the end of August until the end of April. But here are just some, little snapshots of, this is actually my first big, really big auroral display I ever saw, which was in Fort Yukon, Alaska in 2022. This is actually before I moved up to Fairbanks, and this is what drove me to pursue my PhD at University of Alaska Fairbanks, because I thought to myself, if I'm going to study this thing for potentially 5 or 6 or 7 years, I want to, at least see it. At least see it once in a while. I don't just want to be doing these equations and homework without having any kind of ground truth. So this is a real-time video on the left, and then a still image. I'll just go back to the big spiral, a still image of that video on the right. Okay, so that's a little bit about myself. Now let's delve into the science. So space weather, what is space weather? Well, the technical definition is that it refers to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. But when I tell people what space weather is, I just like to say it's the aurora, because it sort of represents that final step, all the energy from the sun eventually getting to the earth and causing this beautiful light show that we see and that we can enjoy. But it's not just the aurora, obviously. There's so much more going on under the hood. You have shock waves in space, million-degree plasmas on the sun and the sun's atmosphere. You have really cool space missions that are super inspiring, like the Parker Solar Probe, giant explosions, CMEs and solar flares, billions of times stronger than any bombs that humans have ever created. It's just a really exciting field that, unfortunately, people just, I don't think know too much about. It doesn't really get the same press as, James Webb Space Telescope or, Hubble imagery, but the aurora is pretty amazing. And when you really get into why it occurs, you start to learn that there's a lot going on in outer space and with the sun that you may have not heard of before. So it all starts with the sun. Like we have weather here on Earth, there's clouds, rain, wind, and storms. On Earth, the sun creates weather in space, and there are similar analogs in space weather that there are to Earth weather. So the sun gives us warmth and life. It might be 105 degrees in Phoenix or something, and you look up and you're, shaking your fist at the sun, like, why are you doing this to me? But it's the reason why we're all here. And, besides just being kind of an ever-present, fixture of our lives, right? I mean, it's there all the time. Our lives revolve around the sun. We wake up and we go to bed with the sun. It also gives us space weather. So the sun, even though it seems like it's just this sort of static ball of light in the sky, it's dynamic and constantly changing every minute, hour, and day. And this is what gives us the concept of weather. There's this wind that blows out from the sun called the solar wind. And usually it's calm and gentle, but sometimes it can become really strong and fierce. You have coronal mass ejections, which are big explosions of plasma on the sun, and high-speed streams of solar wind from coronal holes. Those are those gusts and those fast solar wind streams. And the actual wind itself carries charged particles and magnetic fields, which bathe the entire solar system in this energy. And that energy can interact with other magnetic fields like those around planets. And Earth has its own global magnetic field, which extends out into outer space, which I'll show you in a little bit, called the magnetosphere. And that interaction between the solar wind and Earth's magnetosphere is how the sun touches all of us and eventually creates the aurora. So let's see if this movie plays. This is just a little kind of highlight reel. I could watch these kinds of videos for hours of different processes on the sun, just showing you that there's a lot going on that you may not be aware of. So you can't see this stuff from the ground because these images are all taken in the ultraviolet. So Earth's atmosphere, thankfully, otherwise we would all be burning up and have skin cancer at this point probably. Earth's atmosphere blocks all this ultraviolet radiation, but if we're in space, we can put special filters on cameras and image the sun's atmosphere called the corona. So you've probably seen a total solar eclipse, or at least a photo of it. That corona is kind of the birthplace of the solar wind, and that's what we're looking at here. And you can see all these different things, these huge loops of magnetic fields. You have these explosions and bright flashes, solar flares. These are active regions. So sunspots you actually can observe from the ground with a solar filter and a big telescope. But these are sort of the magnetic signatures in the sun's atmosphere. Seen here, there's a solar flare, and it looks like a CME launching off right there. There's a big prominence eruption. So, this stuff happens all the time. We just had a big geomagnetic storm a couple days ago, KP8. So, that's a G4 out of a G5. So, that was a pretty big event caused by one of these CME eruptions. These things happen all the time. This is a 4-minute highlight reel, but you could fill hours with these explosions. So all this energy goes out into outer space, and then what happens? Well, it'll just flow out basically forever until it eventually loses its pressure and reaches a sort of equilibrium with, what's beyond the solar system. And it forms this huge sphere called the heliosphere, sort of protective bubble around the entire solar system. But planets themselves, if they have a dynamo in their core, create a magnetic field which then extends out into outer space. And our Earth is one of these planets. And our Earth, this protective magnetic shield is called the magnetosphere. It's kind of like a rock in a stream of water. The solar wind flows past and pushes against the day side of Earth's magnetosphere, compressing it. And then the night side gets extended out, kind of like a comet's tail. And when the solar wind hits this bubble, depending on the strength of the wind, some of the particles, those charged particles, which are riding along those magnetic field lines, can get funneled into Earth's magnetosphere, so kind of hands off that energy and over the polar regions, which is why we get auroras over the north and south poles. And auroras are created in a layer of the atmosphere called the ionosphere. It's one of the highest layers, many times higher than a plane flies, so 15 to 50 times higher. That's around 150 to 500 kilometers in altitude. So whenever someone goes to Iceland or Alaska, and they say, well, I should be able to see the auroras every single night. I say, well, it has to be clear. And I think that's something that has to be said, because a lot of people think, oh, I can see them because they're just like clouds, right? No, they they may look like clouds, but they're way, way, way higher than the clouds that we're used to. So the ionosphere itself is sort of where the gas that we breathe, we're used to N2 and O2. In those upper layers of the atmosphere, it gets so tenuous or less dense that those molecules can break apart into their sort of atomic species like O plus and N2 plus. And that's why we call it the ionosphere, because there's charged particles, and I guess that's considered plasma, just flowing around up there freely. So these charged particles from the solar wind that are riding along magnetic field lines, those get sort of catapulted into Earth's magnetosphere. So now they're in Earth's magnetosphere. They're also flowing along Earth's magnetic field lines. And those field lines kind of converge over the poles. So now you have all these particles rushing in. They're about to slam into Earth's atmosphere. And the first things that they encounter are these, atomic oxygen species around, 500 to 1,000 kilometers in altitude. As you go further down, if you're kind of building this auroral arc from the top down, the gas just gets more and more dense. So if you're a charged particle, you have a certain amount of energy, let's call it 1,000 electron volts, right? As you go down from outer space into Earth's atmosphere, you start encountering more and more dense gas. And when you're colliding with these gas molecules on the way down, you're donating some of your energy to them. And those chemical reactions produce light in specific colors. So, if you encounter an atomic oxygen particle at, 120 miles way up in the atmosphere, that's only a 5 EV reaction. So, as you're moving down, it's kind of like a game of Plinko. You're just hitting all these gas molecules on the way down until you get to a layer that's too dense, where you just give up all your energy in a short amount of time. So if you have more energy, if you're kind of the point of view of the electron, if you have more energy, you're coming down and you're being able to penetrate further into the atmosphere. You're able to interact with different species of gas and produce different colors. So red auroras caused by atomic oxygen being struck by an electron. And then you have this green emission, which is the most common and also the brightest, which is kind of a two-step reaction between nitrogen and oxygen. And then if you have a lot of energy, you're able to make it down to this layer of N2, which is actually the stuff that we breathe. And that's really below 60 miles. And if you have a lot of energy, you're able to excite those molecules and emit sort of a whitish, pinkish light. So that's sort of the precipitation. If you think about the terrestrial weather and the rain that we have on Earth, in the upper atmosphere and with the aurora, you have a rain of electrons coming in from outer space, which we call particle precipitation. And the clouds in outer space, that produce these raining flows of electrons, are kind of like the clouds that we have here on Earth producing the rain that we feel on the ground. So everything that you see with the aurora, it was really created somewhere in the magnetosphere. So that's why scientists like to study it, is because when you look up and you see the aurora, if you see a big swirl in the aurora, that actually corresponds to something happening in outer space to create that shower of electrons that makes it down to the atmosphere. So everything's connected. And I like to say to people, if all this sounds confusing, really the aurora is just like a giant neon lamp in the sky, except for the electricity comes from outer space instead of the wall. And here are just some rare auroral colors. And, I just said that you just get, blue, green, red, and maybe a whitish pink. Well, those altitudinal ranges where those emissions happen aren't just hard cutoffs. There's some overlap. And also auroras are really in 3 dimensions, but you see them in 2 dimensions, right? You're just looking at a plane in the sky. So things can overlap. So you can get green overlapping with red, which can create yellow and orange. If you have really low energy precipitation, like the one here on the left, those particles, none of them will really get to that green layer. So you only have this sort of pinkish, bluish aurora. And there's a little quirk too. If you have aurora really close to when the sun sets, the sun setting, it still is shining in the upper part of the atmosphere. So even though it's dark on the ground, the sunlight is still striking these molecules up here in the ionosphere. So that sunlight can actually ionize N2 plus and create blue emission, which can then mix with the red and create pinks and purples and things like that. Here's another example of that on the right. This was March 23rd, 2023. So almost 2 years ago, we had a really big geomagnetic storm and had aurora right away after sunset and got some amazing colors. So these are just some nice photos I have showing that the aurora is not just green. I think a lot of people think that too, that the aurora is just a green, blob, doesn't really move at all. And once you've seen it, you've seen it. But I can tell you for sure that that's not how it is. And so going to this concept of the aurora ovals, here in Fairbanks, or I guess Alaska, I'm in Anchorage right now, so technically right now I'm a little bit south of the northern auroral oval, but in Fairbanks, we're right underneath that auroral oval. And this is what happens when you just have sort of, the actual reasoning behind why they're ovals and not just like little patches is somewhat complicated, but it has to do with the fact that the geomagnetic and the geographic poles are slightly offset. That just creates these donut shapes of constant auroral energy that persist even when the solar wind is really quiet. So if you travel to underneath one of these auroral ovals, it's going to be a little bit hard to get to Antarctica, but if you go to somewhere like Fairbanks or Iceland or Tromsø in Norway, as long as it's clear and dark, you have a 100% chance of seeing the aurora in some capacity. Okay, let's go over auroral substorms. So a lot of this might have been review if you're into Northern Lights or into Aurora, but substorms I haven't seen a whole lot of talk about, but they're really fundamental to how the aurora works. So over the course of a night, maybe you just have some steady state aurora. If you have a little blip in the solar wind, some stronger magnetic field, you can cause this substorm sequence to start, where you have a charging up of the auroral ovals over time, which can last anywhere from 2 to 3 hours. It's when all this energy gets built up, and then all of a sudden that can be released in what's called substorm onset and expansion. And you can see here on the right, this is an all-sky camera time lapse from Fairbanks, showing just kind of normal aurora, and then all of a sudden, once I press play, you'll see it just explodes all across the sky, but it only lasts like 15 to 20 minutes. That's the auroral substorm. It's the sudden release of energy in Earth's magnetosphere that then manifests in the ionosphere as aurora. So remember, I said, we study the aurora. The whole purpose of studying the aurora is to figure out what's going on in Earth's magnetosphere. So when you have, it's sort of like a bucket of water slowly filling up, and then someone comes over and kicks it over and all the water spills out. Imagine all that water is all these electrons being dumped into the atmosphere. Or another analogy that I use is a big rubber band, full of, if you're ever, if you were one of those kids in class, you would, shoot little paper balls through rubber bands at people. Imagine that paper ball is a big ball of auroral particles. Well, over time in that growth phase, that rubber band stretches out, and those particles are, increasing in potential energy. Then all of a sudden that rubber band lets go, those field lines snap back, and all those particles get slingshotted back to Earth's night side and enter the atmosphere and create this huge explosion of aurora. And this is really crucial, because this kind of determines if you can figure out what phase of the substorm you're in, and whether you're in a growth phase or also after one of these big explosions of aurora. You usually have a 1 to 2 hour kind of cooling down period called the recovery period. If you can figure out kind of where you are, if you are in one of these substorm patterns, whether to stay out or whether you should pack it up. And that's really important. And also for people who are chasing the aurora at mid-latitudes, if you have a substorm, in the auroral oval, let's say that things aren't really that, enhanced, like there's not a big geomagnetic storm, even though there might not be a huge geomagnetic storm, when that substorm happens, you have so many more particles, and I'll show you examples of this, but the entire aurora just becomes brighter, including the very tops of the aurora, which are really high in altitude, like 500 kilometers. Just like you can see a storm really, really far away on the horizon because it's so tall, if you have aurora that becomes really, really tall and really, really bright, well, now all of a sudden people further away from the auroral oval can see that. Even though the curvature of the Earth will block the lower green parts, you can still see the red. So that's how you can see aurora. Like aurora was seen on the very border of northern Arizona 2 nights ago because of one of these huge substorms. So this is really important, because not only does it apply for high latitudes, it happens every single night, 1 to 2 times a night, but during geomagnetic storms, when the auroral oval is a little bit further south than usual, one of these substorms can kick things up and cause you to see aurora only for brief periods, maybe 15 to 30 minutes, from really low latitude places like Arizona, California, Utah, New Mexico, places like that. So yeah, I just kind of mentioned this, but what causes the aurora to be seen at mid-latitudes? Because even though you have a substorm, it doesn't mean that you're going to see the aurora every single night in Arizona. But that's when the sun gets angry. So usually the solar wind's sort of flowing at this steady state, but we can get big gusts of solar wind called coronal mass ejections, which are like sun sneezes, and those launch bits of the sun's atmosphere, chunks of plasma into outer space. And if they're directed at Earth, they could take 1 to 3 days to reach us. So they travel pretty fast. And when they hit us, it's just a huge gust of solar wind. So we have more energy, more particles, higher magnetic field, and that can cause a geomagnetic storm where the auroral oval is actually pushed to lower latitudes. And it's really hard to predict these solar storms. We have the NOAA Space Weather Prediction Center, which is the official space weather forecasting center here in the US. But we also have people like Tamitha Skov, who's one of my friends. And also I do this too, where, we try and, because, a lot of this is really hard. So, I mean, people at NOAA SIPSI, they are the experts, but, it doesn't hurt to have some other opinions, because people say that space weather is like where, terrestrial weather forecasting was in the 1960s. It is really primitive still. So people like Dr. Tamitha Skov, if you want to learn more, she's also a ham radio operator. I need to get my license soon. But she's kind of in this community of amateurs and space weather enthusiasts. She was actually working at aerospace for a while, so she has the expertise, and she breaks down these space weather forecasts that are outputted by NOAA SWPC for their customers, like power grid operators, the military, people like that. They're not really forecasting the aurora, but social media influencers or social media enthusiasts like myself or Tamitha will kind of take what's being put out by NOAA SIPSI and say, okay, what does this mean for aurora possibilities? Because the NOAA Space Weather Prediction Center, a lot of people don't realize this, they may care about aurora chasers, but they just don't have the bandwidth nor the funding to do that. So, and this year, is a really great time to see the aurora, because we're in this period of time called solar maximum. So we may actually be coming down from solar maximum. As you can see here, this is sort of the latest projection by NOAA. You can see maybe the sunspot number has peaked, and the sunspots are kind of a proxy for solar activity in general. So you can see it kind of, well, this only shows one cycle here, or about half a cycle. But if you look here on the bottom, you can see all these different humps. Those are all the different solar cycles throughout time. Going back, it looks like to 1750. So we're in solar cycle 25. And people have been measuring sunspots for hundreds of years. Galileo was one of the first people to notice these sunspots. And every roughly 11 years, we go through a solar maximum where we have more sunspots, more active regions, more coronal mass ejections, and more of these geomagnetic storms. But actually, solar activity and auroral activity peaks are slightly offset. So we should see the peak of auroral activity about 1 to 2 years after solar max, which is, if we think solar max may have been in 2024, well, maybe we should be seeing the peak of auroral activity this year or next year. So it's not the end of the world. You might see this graph and, be a little pessimistic and a little bit sad, but don't worry, the best is probably still yet to come. So now is a great time to be an aurora chaser. And we can predict the aurora kind of, it's hard, right? Like anything in weather, but space weather especially, it is really hard to predict the aurora because there's just so much that goes into it. And we also just don't have a lot of monitors. We only have, a few monitors in space, and there's just not enough data to really make a good prediction. So a lot of it is reactionary. We'll see something in the solar wind hitting us, and then, in 30 minutes that arrives here at Earth because we have satellites a little bit upstream, able to measure these things and beam back the data at light speed. So we have a little bit of warning, but really beyond like an hour, we really just don't know. It's just best guesses. So most websites will use something called the KP index. That stands for K planetary. I just want to talk about this because a lot of people get obsessed over these KP indices and forecasts and the view lines. But it's kind of problematic because it's a global average of activity every 3 hours. And like I was just saying with the substorms, right, we can have a big intensification of aurora that only lasts 10 or 15 minutes. So that won't get captured in the KP, which is a 3-hour average of global geomagnetic activity. It's like trying to say, in monsoon season, you're trying to figure out when a storm is going to hit your house, and somebody gives you, the number 3, and you say, well, what is that? And they say, oh, it's the global raininess index. And you're like, okay, well, great. How does that help me forecast when this storm is going to hit my house? And the person with the 3 says, oh, I don't know. That's like NOAA SIPSI giving the aurora chasing community a KP3, and saying, well, I don't know what this means, but here you go. And then the aurora chasers just assume it means, oh, well, we're going to have, whatever kind of aurora. So that's kind of how it works. And a lot of people don't realize that. So just be aware that the KP index is not the be all and end all. What I really prefer are webcams. And of course, these are most relevant for people up at high latitudes like me and, people in Fairbanks or Iceland where we're seeing aurora all the time. So I always have this webcam pulled up. But if you're in Arizona, maybe you do want to wait until decent, KP6, KP7 storm is forecasted, because chances are you're not going to see anything at a KP1 or a 2. It does track at some point. It's kind of like, if the entire stock market is crashing, your stocks are also probably going to crash. But if you're just trying to look at one stock, you can't use the Dow Jones to, make a one-to-one correlation to what's going to happen with your pick. So, at some point the KP does track, but there are webcams all over the US, and I have a big list on my website where you can tune in and see what's going on. So I always tell people, if you don't want to care about the science, you don't want to care about the KP index or forecasting CMEs, any of that, just go check out the webcams. If there's Aurora on that webcam and it's near your location, well, you're going to see the same Aurora, because the Aurora is huge, right? It's occurring high up in the atmosphere, and these structures are hundreds of miles across. So, I've been on the phone with people. When I was living in North Dakota, I would be on the phone with people in Duluth, which is a city in Minnesota, but about 250 miles east, and we'd be looking at the same auroral pillar and talking about it in real time. So if you see a webcam, and even if it's like the next state over, it's roughly the same latitude as you can use it for detecting aurora. We also have lots of other tools like the Ovation Prime model. This one's kind of nice because it takes what's happening in the solar wind and runs it through a fancy equation, which outputs what the auroral oval should look like. It's a statistical model, so it won't show you when substorms happen, but it will show you in general, if you have better solar wind conditions, you should see a more expanded auroral oval. There are things like the GOES magnetometers, though, that you can use to detect substorms. There's also tools like the ENLO model, which you can use to forecast CMEs, and the Auroral Electrojet Index, which is kind of like the KP. If you just want something that says higher number equals better, the AE index can help with that. Forecasting solar wind, since we're probably looking for CMEs, if you want to see aurora in Arizona, you need some sort of geomagnetic storm to see aurora. You can get a nice substorm at a KP5 or a 6, but that's still a KP5 or a 6, which will require some sort of enhancement in the solar wind that doesn't just happen randomly. Usually have to have a CME to create something like that. So there's a model called the ENLO model, which is used by all the forecasting agencies. It shows the solar wind profile and the model of that from different views, like a top-down view and a side view. There's also this HUXT model, or people like to say HUXT, which is, uses the ENLO model, but outputs the sort of, arrival times of these CMEs and sort of the different parameters in a slightly more user-friendly way, even though this looks like a, kind of eye chart. I actually think this is nicer because it shows you the uncertainty in the models, which is really important. If you see a CME is forecasted, let's say on, April 26th at 12 UT, that might give you some confidence that, oh yeah, those forecasters really know at 12 UT the CME is going to hit. But in reality, these forecasts are plus or minus 7 hours. And, a lot of times, if you see these things posted on the SWPC website, or, local meteorologist is saying that the quote unquote space weather forecasters are predicting an impact tonight, that doesn't really tell you what the CME looked like, if it's a grazing blow, if it's a direct hit, what the uncertainties might be. So this site, the HUXT model, is really good for that. We already talked about the KP index. Here are actually where the observatories are that measure the magnetic perturbations in the ground that go into calculating the KP index. So you can see that, they're all over the world, and, a lot of them are also in Europe too. So like if you have a localized aurora, let's say over Greenland, for example, there's no station there to measure that. So actually that'll just get completely ignored by the KP index. And so a lot of things rely on the KP index. This is my favorite thing, the Chena Hot Springs whiteboard near Fairbanks. They actually just got rid of the whole idea of KP, and now they just say the Aurora Activity Index, which I think is even worse because you can't even look that up. I mean, if you're a tourist and you're like, well, what is this KP index? At least you can maybe at some point figure out that it's not the best thing to use. But now it's just, how active is the aurora? It's a 3 out of 9. Okay, great. People think, oh, wow, it's a 3 out of 9. That's horrible. And then they don't even go outside. But actually a 3 is pretty good. So that's just funny. But, the SWPC website, NOAA SWPC, puts out forecasts for the KP over 3 days. Those are just like throwing darts at a board, honestly. I wouldn't pay too much attention to that. But if you see like a KP 7 or 8 in the forecast, I mean, okay, somebody at SWPC thinks something is going to happen. So then it's worth paying attention to. But if you see like a 2 and a 3 and a 5 and a 4 and a 1 and a 2, I mean, yeah, just, shuffle that up and that's just as good as the last one. The KP index also gets baked into a lot of apps. If you have an Aurora app, you probably have the KP in there somewhere. Then, of course, the news is great at picking up on these solar storms and making their own view lines with, very hard boundaries. Like, oh, if it's a KP6, you should only be able to see it from this little band, which is not true at all. Substorms can push the Aurora and the visibility of the Aurora down to much lower latitudes for a short amount of times, even with the KP being, maybe 5 or a 6. The Aurora oval might be resting above Canada, but if that substorm is really big, you could see that Aurora all the way in, let's say, Colorado or Utah. So you don't need a KP9 to see the Aurora in those more lower latitude states. So we already talked about this. Let's just quickly go over the AE index. It's kind of like the KP index, where a higher number equals better, but it uses high latitude stations. So this is really helpful if you're in somewhere like Fairbanks, where you're actually at high latitudes and you want an index that matters for you. But it does track for mid latitudes as well. So, for you in Arizona, you might want to look for values over 1,000 to where you might want to start paying attention. And these track pretty well with substorms, although it's delayed a little bit. Real-time solar wind is helpful, obviously, because it gives you all the information you need relatively. And you can see, it's measured in, I should back up here and say that we talk about the magnetic field as the letter B, B as in Bravo, and then we have a coordinate system that we define here with a Z and an X and a Y. What matters for Aurora is BZ South, because Earth's magnetic field flows out from the South Pole into space and then down through the North Pole. So if you kind of do that motion with your hands, your arm is physically moving from the bottom to the top. So that direction is BZ north or BZ positive. So if you imagine bringing two bar magnets together that are opposite in polarity, if you have a north, which is always what Earth's magnetic field is, and a south, those two will attract, and you can get energy that transfers from the solar wind to Earth. And that's how we get the substorm cycle to start up. And also you can get substorm expansion, which is when the Aurora really intensifies by when the BZ turns, it's called a turn, from south to north. And so I have this whole ebook. If this is all confusing and you need some reading material, I'll have this QR code later, but I got this ebook that's free, actually. It's like 60 pages. I just wrote it during my winter break, and it's got a bunch of information on how to look at the solar wind, but that's an entire hour-long presentation in and of itself. So I'll just be kind of glossing over that. If you don't want to read the solar wind, the Ovation Prime model, like I said, just kind of bakes in all the solar wind, puts it through a fancy equation, and you get a nice Aurora oval, which also tells you the quote-unquote power of that Aurora in gigawatts. So yeah, there is a lot of power in the Aurora, actually. Hundreds of gigawatts. I think there was actually a mission, I don't know when it was, probably 30 years ago, that tried to fly a little EMF generator through the Aurora to see if the U.S. could harness power from the Aurora, but that didn't quite work out. But if we could power the country for days or weeks with just 10 or 20 minutes of Aurora. There's a lot of power up there. So this is kind of a really friendly model, but again, it's just a statistical model, so it's not actually showing you where the Aurora is, just sort of where the likelihood of seeing the Aurora would be. And also remember that during substorms, which are not captured by this model, you could see Aurora further south. All right, so forecasting auroral substorms, you can use a lot of different tools. One thing that I like to use is this GOES magnetometer. And you just look for these spikes in the graph. Those correspond to when the rubber band is releasing, and you have a huge flow of particles from the magnetotail to the night side, causing this big intensification in the Aurora. I'm going to kind of go a little bit quicker here because I know that we're already at Q2. But, the best sort of data set that you can have is ground truth data, right? You can have all these fancy graphs, equations, and that's you guys. So there's sites like Aurorasaurus where you can actually report if you've seen the Aurora or not, and those get put onto a map, and you can track that over time and see where people are physically seeing the Aurora and have made a positive report. And there are webcams as well, like I was saying. This is just kind of a cool example of using webcams to figure out where the auroral oval is in real time. This was during the October 10th storm in 2024. Maybe you all saw that down in Arizona. I think there was actually some nice SAR arc activity from down there, but you can see here a camera in Maine showing the Aurora to the south and a camera in Georgia showing the Aurora overhead and to the north. So somewhere in between is where the auroral oval was resting. And there's multiple different timescales on which you can do forecasting, hours to minutes to days. It gets less accurate as you go out in time. And so here's sort of my aurora chasing workflow. At high latitudes, I have to figure out if it's cloudy, if it's dark enough, and then I just kind of try and forecast those substorms. And it's the same at mid latitudes, except for you're waiting for, some sort of CME activity, some sort of CME impact or enhancement in the solar wind to get that aurora oval just a little bit further south. And so, yeah, this is what I was talking about, a big SAR arc, the stable auroral red arc. Actually, it's a really rare type of subauroral phenomenon, so it actually forms south of the auroral oval. This was photographed in Arizona just in October. All right, so let's blast through some aurora chasing tips and tricks. All you need is a love for the night sky and some patience. People have been talking about the Bortle scale all night. You are all familiar with this, so I don't need to tell you, but you want dark skies to see the aurora. It's going to look very different depending on where you're at. I mean, if you're in Arizona, you're probably not going to see a big auroral spiral like this. This is kind of exclusive to the high latitude locations, but one tip I have is if you don't know what it is, just take out your smartphone and take a quick test shot. You might be able to see something with your phone. And red aurora glow is really common from lower latitudes because you're actually seeing the red tops of the aurora from further away. You're not able to see the green because the Earth is sort of blocking that from your view. The Earth is round, of course, and you're not able to see the very green bottoms of the aurora, even when they're there because the Earth is blocking it. So this is just an example. During a substorm, I was actually in India last year in May during the largest geomagnetic storm that we've had in 20 years. And I saw the aurora pretty close to the China-India border because a big substorm pushed the aurora really high, and I was able to see that from my perspective. And of course, the auroras will not look the exact same on your cameras as they will with your eyes. Things will be a little bit more muted with your eyes than on the cameras. There's tons of variables that affect this, but I will say just that, eyes and cameras work differently. We have rods and cones, cameras have pixels. And so below a certain light level, our eyes just cannot see color, and that's just how it is. But you can also kind of biohack the aurora, and I'll have you look at this down here at the bottom left. If you cannot see the green, I won't tell you what it is, but if you can't see the green in this circle, you have a little bit of color blindness, which could actually affect your ability to see the aurora. A lot of people don't realize it. I've actually had a couple friends come to me and say, yeah, I've just never seen the green in the aurora. I just don't know. And I'll show them, a color blindness test like this, and they say, am I supposed to see something there? And I'm like, yeah, buddy, you got some color blindness. That's probably why you can't see the greens. So if you can't see the green in the aurora, it could be for a lot of reasons, but your cones, which see color, need a little bit of light to activate. And you can actually, it'll ruin your night vision, but shine a flashlight in your eyes, and that causes the cones to activate for about 10 seconds. You can just look away from the flashlight, look up at the aurora, you'll be able to see the greens just fine. So now aurora photography, really anything can do it nowadays. If you have a night mode on your phone, that's good enough. But for DSLR mirrorless cameras, 5 to 10 seconds, lowest F number, ISO 16 to 6400, and shooting manual mode is the best way of doing things. Auroras are hard to photograph, right? For astrophotography, Milky Way photography, it's pretty, I don't want to say easy, but you more or less choose your shutter speed and it never changes. But with auroras, it's constantly changing in brightness. It'll just get really, really bright during a substorm, so you're going to have to respond. And I always tell people to adjust the shutter speed versus anything else. You want your aperture as wide as possible all the time. And this is just an example of how bright the aurora can be. This is 1.6 seconds at ISO 640 on my Sony A7 Mark IV 14 millimeter f1 or 20 millimeter f1.8 lens. I'm going to skip the little time-lapse video, but time-lapse photography is a really good way to just set your camera up and take a bunch of shots, and you can capture everything. You don't have to worry about missing the show if you set your settings right. And to set your settings right, what you really want to do is underexpose a little bit when you're setting up your camera so that you can account for any brightenings in the aurora from a substorm. And I have this blog article on my site, or you can ask me after the talk if you want to learn more about this, but just some general settings too. You want to have your shutter speed a little bit quicker than usual. I tend to use auto ISO. Actually, in newer cameras, this works fine. People are, rightfully afraid of auto ISO because back in the day, the meters inside cameras were not that good. But nowadays, they're great. And I usually try and get 240 photos at least if I'm playing this back at 24 frames per second. So I have a 10-second total movie length. And so here's my editing workflow. I was listening to the talk about AI. I am using the AI denoise in Lightroom now in my processing. So that's what I have down here. There's also this neat video plugin that I don't know if it uses AI or it's just some fancy algorithm, but it may have been updated to include an AI algorithm, but that also further removes noise as well. So I use a combination of LR time-lapse, which is actually a free software. It allows you to process up to 400 shots, and then that links up with Adobe Lightroom Classic. And then you can use Adobe After Effects, Final Cut, any sort of processing software to take a JPEG sequence and turn that into a movie. But I just use After Effects. That's what I'm used to. And what I've been really doing recently, if you follow me on Instagram or anything else, I mainly just post real-time videos because it's super easy for me to, take out my Sony a7S III and just, go outside and start recording. And I really recommend investing in a really nice lens because that matters the most when you're trying to get as much light as possible into your camera. And the Sony a7S III is still the king of real-time video. It's 12 megapixels and it's a full frame sensor, so those pixels are huge. Just some kind of more, about the sort of more nuances about real-time video. I underexpose a little bit. The ISO is going to be crazy. You're probably looking at this and saying, what the heck? But yeah, 128,000 for the ISO. I will be up there when it's a new moon and there's not much aurora in the sky. It is just really, really dark. And I can still shoot video and get relatively clean shots after I've cleaned it up with neat video and After Effects at ISO 128,000. But it does help to have a full moon. So if you're trying to go to Alaska or somewhere else and you want to take a real-time video with the camera that you have, most cameras can do it as long as there's a full moon and the aurora is really bright. But if you do want to get really crispy, clean video, you'll want to invest in a few cameras that are specialized for these low light situations. All right, I don't really have time for show and tell, so I'll just breeze through this really, really quick because I want to be able to have questions after. There's this, it's not technically an aurora, but it's called Strong Thermal Emission Velocity Enhancement, or STEVE, that I photographed in North Dakota in 2021. This was the night that blew me away, March 5th, 2022. So I showed you that auroral spiral that I saw from Fort Yukon, Alaska back in 2022. That kind of inspired me to move to Alaska and go to school. This is that same night. And this is that winter trip to Churchill in 2022, really awesome auroras there. And then again, I went to Churchill. I was taking a gap year, so there's no way I could have done this now with classes and everything going on. But just some fantastic stuff. And then we had this big auroral substorm. So this is what I mean by, things can change in an instant. Boom, right? Just massive, sort of explosion of aurora there. That's what a substorm looks like. And then I need to update this, but I've been shooting mostly real-time videos. So I think these were kind of the last photos I ever took this season. But I think I looked back and I have about 500 gigabytes of real-time video, and those are all like 10 or 20 second clips on my Sony a7S III. I have a folder on my iPhone that just says real-time video, and I checked it today and I have 2,800 videos in that folder from 2022 onwards. So I see the aurora a lot. I try and go out as much as I can, and it is part of my life, and I guess why people call me the aurora guy. So thank you for your attention, and I guess we have some time for questions.
Question, Vincent. You mentioned that the aurora cycle is out of phase with the sunspot cycle by a year or so. Is there an
Correct.
easily understandable reason for that?
Yep, it's kind of twofold. So as you go along in the solar cycle, the sunspots start to appear lower in latitude. And if you think about those sunspots as like cannons and those cannonballs as CMEs, as they're moving lower in latitude, so closer to the sun's equator, those CMEs are going to be launching more at Earth instead of above or below the equator. So that's one reason. And then as you go through the solar cycle, these things called coronal holes tend to become more prevalent on the declining phase. So when you're kind of right after the peak on the declining phase, you have the combined effect of still quite a bit number of sunspots plus the coronal holes now opening up, which gives you just more activity. You have the combined effect of these high-speed streams of solar wind plus the CMEs.
I'm curious as to why the red auroras aren't more common, given that they use less, they require less energy than the green ones.
Yeah, that's a good question. The red auroras, I would say, are not as common because the density of particles and at those higher altitudes is so low. So if you imagine the auroras coming down from outer space and it's just not interacting with a lot of particles, there's just not a lot of light that's going to be produced. As you go lower in the atmosphere, it's like an exponential increase in density. So if you reach a certain point, even if that particle doesn't have a lot of energy to begin with, it might just deposit right there in that lower layer because that's where the gas is densest.
You mentioned in one of your slides that to take pictures, it's better to have the moon. I'm surprised because I thought the moonlight would drown out the aurora.
Yeah, so I'll go back to that if I can. So yeah, I mean, it's a little bit nuanced, right? I would say that there's never a bad time to see the aurora or to photograph it. If you're trying to do a real-time video, you really want the moon because you're really just, you're at the limit of what cameras can do. I mean, you're at 1/25th of a second. Imagine trying to take a Milky Way photo at 1/25th of a second. No matter what lens or camera you're using, it's just going to be hard, right? So if you have a moon, there's just more ambient light for you to get more light and more exposure. Now, if you're using a longer exposure, you're just doing regular photography. I personally like having no moon, so a new moon for that. Because people, this is all personal preference, but whenever I show people photos, I wonder if I have any here in this show and tell. These might all be new moon, but whenever I show people photos of the aurora with a full moon, they always say, "Oh, why was it taken during the daytime?" Or when they see the moon, and my mom has said this to me so many times, she's like, "Oh, how is the sun up at night?" And I'm like, "No, that is just the moon." People just get confused, and when you have the new moon, you can actually see the aurora and the light from the aurora showing on the ground, and it turns the ground or the snow green. I think that's really cool. Whereas when you have a full moon, that just doesn't happen because the moon is too bright, unless you have a really, really powerful aurora. So I would say, yeah, if you're just trying to do regular photography, come during a new moon. If you want to just do smartphone photography or real-time video, or you just want to care about the viewing experience, then come during any time or maybe a full moon.
All right. Well, thank you, Vincent, for joining us here tonight.
Thank you.
We really enjoyed your time with us, and awesome presentation. I really enjoyed it. So anyway,